All right, sure.
Welcome everyone. I'm very happy to have Subho with us today. He works in AI and specifically trustworthiness of AI. He also has an expertise in large language models and has awards from the International Indian Statistical Association, which the name is a bit confusing, honestly. He is currently the chief of AI at this startup, Vijil, and he wants to come back to India. So with that, let me give it to him.
Thanks so much. Thank you, everyone, for being here in my talk. It is really an honor and a privilege to be presenting at TIFR. Thanks so much, Raghuvansh, for the invite and organizing the talk as well. So as the title states, today I'm going to talk about the statistical foundations, one problem regarding the statistical foundations of language models, specifically the problem of consistency, and more specifically, the problem that language models, large language models, and small language models, they're not that robust or consistent in the sense that if you tweak inputs to a language model a little bit, their output can change a lot. And the reasons for that are rooted in the robustness problems that all learning systems have faced, starting from very simple statistical models that hasn't yet been solved and continues to get less and less attention as learning systems grow more and more complex. So this talk is an attempt to give some ideas that can bridge the gap to lay the foundations of robustness in language model research. And the reason I start with my background is that this background was kind of instrumental in making me think deeply about the problem and trying to bridge the gap between the two concepts of robustness in statistical models versus consistency in language models. Some of my early work is on robustness, which I'm going to talk about in the first half of this seminar, diving deep into one of my past research projects in collaboration with somebody from ISI Kolkata. And then later on, I'm going to connect, at least conceptually, to the notion of consistency and reliability in language models, which continue to be a focus of my current research, one of the current research directions that I want to take forward in the next few years. The broader vision of research I have is kind of two-pronged. Firstly is new methods for defending AI, mostly because methods for defending AI continues getting less attention in the research sphere as of yet. So there is a lot of interesting problems sitting there and a lot of work to be done, a lot of impactful work to be done. On the other side,
what does it mean to defend AI?
Good question. The reason, the overall definition is that even though language models are showing a lot of good applications, they are vulnerable to a large and diverse group of failure modes, which include reliability notions like robustness that I'm going to talk about today, which include security concerns, where language model inputs and outputs can be hijacked by malicious actors to make them do things that they were not designed to do initially and propagate downstream harm, and also safety concerns like bias and fairness and toxicity. Again, function of the training data, large-scale training data that language models have been trained on, which have to be mitigated post hoc for applications that are built on top of these models to behave in a safe and secure manner in deployment. So to wrap up the motivation, I'm going to focus on the notion of robustness and consistency in both statistical models and language models in two different directions, in two different projects, and then finish with a couple of open problems that exist in the intersection of these two projects, project number 1 and project number 3. And sort of give you guys some ideas, some motivations that, hey, these problems might be something cool to work on as well. Very happy to chat later on. Also, if you think about, if you end up thinking about some ideas as well related to these directions. But before that, let me dive into the actual, the meat of the talk itself. So the first project, this was published quite a few years ago. And back then, this was actually the very first method of doing robust and sparse high dimensional regression. So think lasso, think L1 penalized learning problems. So after this paper laid down the foundations of how the theory of robust inference in high dimensions looks like, a bunch of work built on top of that. This work was done in collaboration with Avik Ghosh, who is right now an associate professor in ISI Kolkata, and he's the student of Arup Ghosh, who is an influential figure in the area of robust statistics. The setup that we are going to take forward is that of a standard linear regression model, y is equal to x beta plus epsilon, with epsilon being IID, standard normal errors. What we are going to work with are sparse estimators of the coefficient vector beta, where the learning problem we are going to solve, the loss function we are going to minimize, is a penalized loss function, which consists of a loss term, like squared error loss, and a penalty term, which basically penalizes elements of, penalized based on sparsity of the coefficient vector, so as to enforce exact zero values in certain elements, in one or more elements of the coefficient vector. As most of you folks probably know, these kind of high dimensional setups are useful in a lot of applications, especially in biomedical domains, where, for example, you want to determine that what genes or what single nucleotide polymorphisms are instrumental in a certain output, phenotypical or genotypical outcome, or certain disease outcome that you might be observing through retrospective study or retrospective study or controlled study. So because of that reason, sparse estimators are useful.
Do you have any problems due to the fact that the notion of sparsity is basis dependent? If you change the basis of representation, a sparse vector may no longer be sparse?
Sorry, basis dependent meaning, are you talking about like group sparsity?
No, as the vector you can represent it in different bases, using different, like a you can rotate and get a different coordinate. These L1 methods are adapted to that specific basis, which were difficult. Yeah, that's what I'm saying. Like, if you just maybe if you have a different basis, then you have a different. Then you will rotate the L1 ball so that those basis vectors are a fixed of the ball. But you have to. My question is how do you determine the right basis? Oh, okay. That's a problem specific. It's problem specific. Like if you want to minimize the number of genes or something. Yeah, I think the measurement basis is.
So the problem in basis related problems in high dimensional situations is that problem in high dimensional situations is that the design matrix is, and by definition, ill conditioned. It's by definition reduced rank, and so the basis matrix is not going to be full rank. And so because of that, the conditions generally we assume are not the typical x transpose x divided by n goes to a positive definite matrix, but something weaker. And there are different versions of these conditions, but more or less the conditions boil down to a relaxation of that x transpose x divided by n goes to c, which is, and that is based on the sparsity of the beta parameter. So essentially, among the sparse coordinates of the beta parameter, that restriction or that limit holds. That's sort of the overall notion of the design metrics that we want to take forward. I'll touch upon that a little bit in a couple of slides.
Okay, and one last thing, what are you calling amongst all these variables? What is the design matrix?
Sorry?
Amongst these variables, which one is representing the design matrix? X.
Oh, design matrix is X.
Okay. Okay.
All right. So to give a little bit of overview of the state of the art in non-robust sparse estimation, lasso is a fairly popular method where you do an L1 penalization on squared error loss function. There is also a smoothly clipped version of the L1 loss function, which is called SCAD. That's basically becomes a constant penalty function beyond a certain threshold. Before that, it's the L1 loss. And that has some good properties that reduces the bias of the resulting estimator in certain situations. But these estimates are all non-robust. And the motivation of the current work that we, the reason that we decided to do this are initially threefold, and then the fourth motivation is, I think, more important, which later we realized. So the first few motivations are fairly standard, that it felt that robust inference for high dimensional sparse situations, literature on that was quite sparse. There were either purely empirical techniques or purely theoretical techniques with nothing in between, nothing bridging the gap. And so we thought that, hey, this might be something useful and impactful to work on. But the other reason, once we dove deeper into the problem, came out is that most of the methods that we had seen in the literature until now, they actually assume non-robust design metrics, in the sense that the same kind of conditions that we all know have been used for standard linear regression, for example, this that I mentioned before, or sparse regression. These are the conditions that people are using to do a robust estimation, to propose methods for robust estimation in this situation as well. That didn't quite make sense, in the sense that if I'm not assuming any robustness conditions on the design metrics, then I'm not actually taking into account the situation where outliers can exist, where data contamination can exist in the input data set of a learning problem. We are just taking care of output outliers. In that situation, in the presence of input outliers, these methods are not going to work. So that became a big motivation of proposing our sort of more general framework as well. Just stopping a little bit on the restricted eigenvalue condition, because this is the relaxation I was talking about before. Looking into this, this is basically saying that, okay, for certain sets of beta, you have a condition that is similar to this more stricter condition that holds for a full rank design matrix, which is useful when number of samples is higher than number of parameters. On this situation, this is high dimensional. So of course, number of samples is much, much, much less than number of parameters. And in that situation, the best we can do is assume some kind of relaxed condition, and also assume that this coefficient matrix is somewhat sparse. This shouldn't be dense. In that case, identifiability is not going to be there. This is sparse, and hence we can faithfully estimate some of the elements, the sparse elements, the non-zero elements of the vector beta based on this relaxed condition. So in this current problem, the loss function that we are taking is quite important. The loss function we're considering is quite important. This is called density power divergence, which is a generalization over the KL divergence. And the core idea is that this tuning parameter alpha varies between 0 and 1. When it is closer to 0, you get a more efficient, more accurate estimator of the quantities beta and sigma. Sigma is the scale parameter, the standard deviation or variance parameter, and beta is the coefficient vector. So when alpha is small, think this is, yeah, this should be other way around. Sorry, this is a typo here. So when alpha is small, the estimator is more efficient, less robust. When alpha is 1, it's other way around. And when alpha is exactly equal to 0, the estimator coincides with the negative log likelihood loss. So basically, this also generalizes over log likelihood based estimation. So MLE, basically maximum likelihood estimation. So the minimizer of the DPD loss function at alpha equal to 0 is exactly the same as the maximum likelihood estimate. And small quip about these parameters, don't get put off by these. This is just the standard normal loss function with a bunch of extra terms. All right, so when we add a penalization on this, simply a penalty term gets added, which can be the standard lasso L1 loss function or the SCAD loss function, which is the smoothly clipped absolute deviation being a very good example of that. And again, when alpha goes to 0, this becomes the standard penalized negative log likelihood loss function. So how do we know that the resulting estimates are actually robust? We know that through using something called influence functions, which is a classical tool from robust statistics from the 80s that basically measures the amount of limiting bias due to contamination that can exist in the data. So the idea is that consider a true data distribution and then consider a joint distribution of that true data distribution and some Dirac delta distribution that places a very small amount of mass far, far, far away from the actual data distribution. And so based on that, the influence function of a functional of the data distribution. So here the functional would be the parameter estimate beta or the scale estimate sigma. The influence function of that would be the value of the same function in the contaminated data distribution minus the value in the actual data distribution divided by the amount of contamination and let the contamination go to 0. So this becomes kind of like a partial derivative. So that's the idea, that influence function measures the limiting amount of change or perturbation a contamination can bring in to a certain estimator, certain functional of the data distribution. And so the idea here is that if a certain estimator is robust, then this influence function is going to get capped. It would not be the case that if the amount of contamination keeps on increasing, the amount of change in the parameter estimate itself will also keep on increasing. It has to be bounded at some point of time so that you have some amount of guarantee that, okay, the quality of the resulting estimate is not going to degrade beyond a certain amount if more and more and more noise keeps on creeping into the data set.
So this is going to be for vanishing contamination. So it's not the setting of constant traction.
Yeah, exactly. So it has to be vanishing contamination. Yeah. So now, if you look at the influence function for the DPD estimates, you can actually see that they are bounded. So just a little bit of side-by-side comparison of the influence function of the coefficient vector beta and the coefficient vector and the scale estimate, scale parameter sigma for the MLE. So for alpha equal to 0, which is the MLE, versus for alpha equal to 0.5, which is the DPD estimator at alpha equal to 0.5. So if we look at side by side, we see that the influence function in the first case for both the parameters beta and sigma are unbounded, whereas the influence functions are not unbounded. For alpha equal to 0.5, they go up and then go down and become kind of sort of constant after a certain magnitude of deviation from 0. So this gives us an idea that, okay, this is going to work as far as robustness is concerned. So I mentioned before that one of the major things that we found out that existing methods are using just standard conditions on the design metrics. So how are we changing it? And based on that, what results are we proposing? I'll touch a little bit on that. So the restricted eigenvalue condition I mentioned before, there are many flavors of that. This is one of the flavors that we decided to generalize around, which says that for a certain set of parameters with a certain sparsity property, this condition holds. And so what we did was append the cross product term in the middle with the Hessian of the robust loss function. And the reason we did that was based on the influence function intuition, because in this situation, pending certain constant terms and scaling factors, what this boils down to is the cross product of the two influence function vectors. And so if the influence functions are themselves bounded, then it's expected also that this element, the eigenvalues of this element, are also going to be bounded and well-behaved enough so that the resulting estimates of beta are quote unquote identifiable or estimable within certain error bounds. That is a function, that is a decreasing function of sample size. So kind of sort of root and consistency. That's where we want to aim for. And so working backwards from that, we propose this generalization of the restricted eigenvalue condition. And if you take this condition and go forward, what we'll end up with is a bound on the quality of the estimate that this is going to be beta hat S and beta star S, not the hat is a typo. But the idea is that there is going to be order of log n by kind of sort of root n, little bit worse than root n amount of error between the true parameter and the parameter estimate in L infinity norm in beta and just normal absolute norm in sigma. If we generalize conditions, if we make the conditions stronger, the assumptions stronger on both the design metrics and the loss function itself, then the rates improve and become root n. And of course, since beta itself is sparse, the convergence rate is going to be dependent on the amount of sparsity that beta has. So basically, the more sparse the coefficient estimate, the more sparse the true coefficient is, the more accurate your resulting estimate going to be. And then it's the other way around. So less sparse, less accurate, and varies according to square root of the amount of sparsity. Next level, if you make the conditions even stronger, you get to asymptotic normality. So here, we don't really infer anything about the asymptotic distribution of the parameter estimates. Here we can, based on stronger and stronger conditions, again, on the loss function and the restricted eigenvalue type assumption on the design matrix. The computational, sorry, go on.
So maybe miss something. So how did this improve anything about the robustness? Because there's just one quantity, right? But what is so you mentioned the influence function value. So is there any bound on that here, or what's going on?
So there is no such effect on the robustness parameter itself on this, apart from the fact that how much that concentrates this quantity or not. So if you are imposing more robustness, that means that your final estimates are going to be a little less accurate based on this condition. And if you impose less robustness, that means the final estimate is going to be more accurate. So the asymptotic distributions that you get here are going to be more concentrated. But on the other side, you're more likely to lose out on the robustness aspect as well, based on influence function analysis, for which we have a few results as well. So, and the influence function related results would be exactly that. What is the amount of what's the upper bound of the magnitude of the influence function going to be? That is going to be dependent on the robustness parameter alpha. Does that?
Yeah. So that bound you will tell us about later. So the
Sorry.
So the bound so the upper bound on the influence function that you will tell us about later.
That is in the actual paper. I am going to not get into that detail because I want to talk about the second paper as well. But you can check out our paper to learn more. All right, so the computational algorithm for this is fairly simple. It's a simple block coordinate descent algorithm. You first optimize over beta, and then you first optimize over sigma. What you see here is called a concave convex procedure. It's nothing but an approximation, a first order approximation of the penalty term, which, yeah, it is a first order approximation of the penalty term, which consists of a concave function and a convex function, which is the exact L1 penalization. L1 penalization plus the first derivative of a function, that is penalty function minus the L1 penalty function. So you use that that to do the update for beta, and you use the resulting beta hat to update sigma using Clarence simple gradient descent. And what that looks like exactly is this: is that given a certain beta hat k and sigma hat k, I'll mention what those are exactly in while doing the implementation. But that's the idea, that at a certain iteration k, you take the corresponding estimates, plug them in to the actual loss function, take an argmin of that to get the next iteration of beta hat, plug that in to get weights, and then plug those weights in to obtain the scale estimate for the next iteration as well, and iterate until convergence. There is a tuning parameter selection problem, which is choosing the tuning parameter for the penalty function. For that, we use a standard high dimensional Bayesian information criterion, where the idea is that the parameters, based on the number of parameters and number of samples, you penalize the amount of sparsity in the parameters. And also you have a term that takes into account the scale factor as well. So grid search over a number of parameters that minimizes the Bayesian information criteria, the HBIC, with the grid values being dependent on the sample size.
Hi, so where is lambda in this?
So lambda is the tuning parameter in the penalty function.
No, I'm just saying that in the equation 1, there's no lambda on the RHS.
Lambda on the RHS. This one?
No. In equation 1, so you're defining HDIC as a function of lambda on the left side, right? But on the right side, I don't see any lambda.
Aha, okay. So here, beta hat and sigma hat, these are obtained from this iterative algorithm, right? And this has a lambda sitting here. So this is really an abusive notation that I did. So these are actually also dependent on the value of lambda as well, these solutions that we're getting. So for each given lambda, we compute beta hat, sigma hat pairs, and then choose the beta hat, sigma hat pair corresponding to the, yeah. Okay, so some amount of experimental validation. For that, we generated 100 samples corresponding to a certain correlation structure. Set a few elements of the coefficient matrix to 0. There are a couple of settings of this that you can check out in the paper. One, a strong signal setting, another a weak signal setting. Then generate random errors, and then consider 3 settings of outliers. Input outlier, output outlier, these are switched, but output outliers is add 20 to each output. Input outliers is add 20 to some samples, some rows of some samples in the design matrix, and then no outliers. The no outlier setting is there to just make sure and check that how much are we losing out, if any, corresponding to as compared to non-robust alternatives as compared to L1 penalized alternatives as compared to other competing methods. The estimation metrics, the comparison metrics that we use are these. For beta hat, we use mean squared error, estimation error, and then root mean squared prediction error. True positive rate, true negative rate, sparsity, these are checking what proportion of the true non-zero coefficients are we detecting. So true positive is what proportion of the true positive non-zero coefficients are we getting. True negative is what proportion of the true zero coefficients are we getting. And then mean sparsity is the number of non-zero coefficients are we getting, which should be more or less exactly same most of the time to the true number of non-zero coefficients. And then finally, estimation error for the variance term as well. Experimental results for output outliers. This is going to look about the same for all 3 outlier settings. But the long story short is that our method is doing well compared to other methods, which is DPD lasso. So in place of non-convex penalty function, if you use lasso, this is what happens. The optimization is not that stable. You can use lasso on log DPD as well. That is from a previous technique. Our proposed method does better than that as well. Compared to non-robust methods, of course, it is expected to do better, and it does better. And also a bunch of algorithmic techniques, which also it does kind of sort of better. Especially RLRs, I'll mention specifically because the initialization of the block coordinate descent algorithms that I mentioned, those initializations were based on RLRs, which is a robust version of LARS that is a method of an optimization method for the lasso problem that people have proposed before. So we took the RLRs estimate and ended up improving on it a little bit. In presence of input outliers, also the result is kind of sort of the same. The idea is that here, based on different values of alpha, you can get slightly different results. Remember the trade-off between robustness and accuracy. So because of that, the variation over alpha happens. And then finally, the non-robust situation, sorry, the no outlier situation. In that case, our method is it's good that the proposed method does not lose out too much as compared to techniques like SCAD or MCP, which of course perform well because there are no outliers in the data. But the DPT-based methods do not do that badly. So that gives an idea that, okay, we are not losing out on efficiency as much while trying to account for robustness in this setting. So that brings me to the end of this specific work. I'll move on to the next project, but before that, I'll take any questions if there are any.
Yeah, so one more. So could you please go back to the slide where you had the results for the DPT, the theorem? Yeah, so here you say that under the conditions we prove that beta hat SC is 0, which means that you're recovering the support exactly.
Yeah.
So so which means that if you're able to recover it exactly, then essentially you're able to solve the problem without sparsity. So basically you have a small number of coordinates. So essentially then you're able to reduce it to a low dimensional problem in some sense, and then you are doing some kind of robust regression, right? So I'm saying that if you have identified the coordinates correctly, then so if someone told me what is that coordinates were, then the problem is just one of robust regression, right? After that.
Yeah. But the issue here is that these two things are interrelated in the sense that while inferring for the non-zero coordinates, we are using the same optimization technique to estimate the values of the non-zero coordinates as well.
Actually, I think my point was that so at the end of the day, you want to bound the inference function. And what is telling you is that that the inference function computation will somehow have this nice feature that you have found the correct coordinates. And so it's not really correct that so if you find the correct coordinates, then I could just essentially prove using some other tools for regression, some bounds, so basically. So
yeah,
does that work?
Yeah. I think I understand. So the core problem is that yes, you are inferring the non-zero coordinates exactly, but the process of inferring the non-zero coordinates exactly is the exact same process of also determining the value of the non-zero coordinates as well. But for very high dimensional cases, there are actually coordinate-based methods which lets you filter down from say thousands of parameters to hundreds of parameters. So it is actually possible to filter down the non-zero coordinates to a very small set and then do this kind of optimization on top of that, which is not reducing the amount of non-zero coordinates that much after the first filtering step. So there are methods like that as well that people use in real life, like in applications also.
Oh, okay, thanks.
All right, so moving on, let me do a little bit of a primer on large language models. I won't dive into too much details because I saw that the previous speaker, Pranit Netrapalli, last week, he did quite a bit, talk about quite a bit about how language models work. So as you all might already know, most of the language models nowadays are autoregressive models, which do next token predictions. And they are trained on large amounts of text data, and basically, given some amount of text, they predict what is going to come next. And more or less, the way this works is that given some amount of text, say a question, that the words in that question get broken down into tokenizers, which gets fed into the neural network as a tensor of one-hot encoded vectors, and one-hot encoding would take into account each of the. So one-hot encoding would be a bunch of 101010 vectors, where one corresponds to a token, roughly corresponds to a word or part of a word, and 0 would be everything else. So that encodes the input data, feeds into the neural network, and predicts the probability of all the tokens being the next token. You pick the most likely token that can be the next token. There is a sampling step involved, which changes things a little bit, but roughly this is the situation. And then you keep on continuing. Add back the token generated and generate again. What is the shape of the Earth? The Earth is round. And this is solely a function of the next token probabilities. And the guarantee that the answer is correct is dependent on the guarantee that these probabilities come in the correct order that makes sense realistically. So roughly, that's the way the language models are trained as well. Take a lot of data, encode them as one-hot encoded tensors, train the neural network based on the patterns encoded in that data to make sure that the empirical loss is minimized, the loss of predicting next token probability on these known samples. So the issue here is that the end probability, the end predictions that we're getting are next token probabilities. And these next token probabilities are the sole determining factor, which is good and bad in the sense that if you have good quality data, these probabilities would make sense. If you have bad quality data, these probabilities might not make sense. If you end up training on a lot of bad data, then it might be that in those situations, these probabilities are reversed. And in that case, you end up predicting the Earth is round. So that exact situation is at the core of a lot of problems current generation of language models have, the trustworthiness problem that I mentioned earlier. And those trustworthiness problems can come in the shape of reliability, security, and safety. The reliability aspect is what I'm going to focus on going forward. But before that, one small amount, a little bit of fine primer on the concept of LLM fine tuning as well. Fine tuning is the process of adapting a pre-trained language model for a specific task. For example, if you are taking a pre-trained model that is trained on a bunch of generic data, it's very less likely that it's going to perform well for a certain task. For example, writing a diagnosis based on a large amount of doctor's note in medical data sets. So for that, what people do is fine tune based on domain specific data. So if you want to use a language model to write a diagnosis report for a bunch of medical notes, fine tune that language model on a bunch of medical notes and the generated diagnosis report and their respective generated diagnostic reports. Once the language model knows enough of that pattern, it will be able to generate reports that make sense. So that's the overall idea of fine tuning. There are different methods of fine tuning. For example, supervised fine tuning, for example, low rank adaptation that I'm going to mention later on as well. So this is context that I'm going to use later. There are trustworthiness aspects of LLM fine tuning as well, which I might mention later on in some other context. But basically, the idea is that just like you can use language models, you can fine tune language models for useful tasks. You can fine tune language models for harmful behaviors like cybersecurity attacks or generating malicious outputs to harm others as well. That is a real concern, which I'll touch touch upon sometime later, hopefully. So what I'll take the next few minutes to go through is the problem of reliability in language models. And the exact problem is that real users do not always ask the same question the same way. Based on different users and their personas and their needs and just random variation, there can be rephrasings of the same question. So just as an example, the standard Khulja Sim Sim question, what can you say to open a door, can be asked in multiple ways. And the answer to this question is actually that there are no such words. This is a completely mythical, this is a question that has a completely mythical context to give a correct answer of open sesame in English. But the correct answer is actually that there are no such words. But when you ask a language model, and these are real outputs from Llama 27B, Llama 27B chat, which is a recent language model by Meta. If you ask different versions of this question, it will actually answer differently in a lot of situations, confirming the folk context of Open Sesame, not answering that there are no such words. So of course, in this toy situation, this is not a real problem, but this can be a real problem in different types of high priority tasks. For example, medical report generation. It is a problem if the user asks, if a doctor asks the same question different ways, and they get back different versions of reports with varying degrees of accuracy. That is not something we expect from a reliable chatbot or a reliable document summarizer. So because of that reason, consistency is a real issue that we need to tackle in the context of language models. So one of my past work, what we did was to propose metrics to measure consistency. And the metrics are actually fairly simple in the sense that they are aggregations of pairwise similarities. The idea is that consider n versions of the same base prompts, n rephrasings of the same base prompts, and consider answers to all the n paraphrased prompts versus the answer to the base prompt as well. Compute pairwise similarities of all possible pairs between these answers and take their average. That's the basic idea. And pairwise similarity can be computed in multiple ways. There can be lexical metrics, for example, token matching based, how many tokens are common between two answers, or there can be more intrinsic semantic metrics that, for example, measure entailment. Answer A follows answer B, or contradiction, answer A contradicts answer B, or paraphrase. These two answers are paraphrase of each other. So that sort of measures the amount of concurrence, the amount of agreement between the set of answers that have been generated from a set of versions, semantic perturbations of the same base prompt.
How do you check this containment?
Good question. Yeah, there are models, NLP models, that have been, again, trained on vast amount of data to score entailment between two pieces of text. So given two pieces of text as input, it gives a probability score that A follows B. And so you can use those models to obtain those scores and use those scores as this pairwise similarity metric.
One question on the same meaning. So when you say these n prompts x1 through xn have the same meaning, is there a way to quantify what that means?
So same meaning wise, the way we quantify is by design. in the sense that normally, experimentally, how we do it is that for some input prompt, we generate versions of that input prompt, knowing that these are the versions that have the same meaning. So for example, pass it through a language model to generate 5 different paraphrases. Tell it that, hey, this is an original question. I want to do this. Give me 5 paraphrases so that you know that they're of the same meaning.
Yeah, so that's like a training exercise. It's not possible to characterize what same means in a more
You could, yeah. You could characterize using some kind of distance-based metrics. So for example, cosine distance or embedding distance, or even having distance. You can set a threshold and say that, hey, below this threshold, I'll consider questions of the same, I'll consider versions of this question to be of the same meaning.
okay.
And then you can sort of inform that threshold using statistical tests and 95% confidence intervals and whatnot. All right, so after we have measured consistency, we also need to ensure consistency. And in a second piece of work, what we did was fine-tune a language model to generate consistent outputs. So what we did was use a prompt template to generate paraphrases of an input prompt. So this is what exactly I mentioned before. Give it a base question, let it generate a number of paraphrases, and then use another prompt template and a highly capable language model to generate consistent responses for all of those paraphrase questions, and then fine tune the original LLM, which you want to make more consistent using these consistent question answer pairs. So now after step 1 and 2, you have pairs of paraphrases and consistent answers. So now you're sort of teaching the original language model that, okay, what are the answers? What are desirable answers to these kind of questions? Overall, the TLDR summary is that this method works. A small example is that when is Earth close to Sun, 2 versions of the question, the base model answers them differently, one right, one wrong. The correct answer is perihelion. The fine-tuned model answers it correctly in both situations. I'll pass on the empirical experimental results in the interest of time. Overall, TLDR is pretty expected that, okay, our method does its job. It makes language models more consistent. But what I will spend 1 or 2 minutes on is the open problems and where can we go from here? And where can we go from here is to actually make progress on this core question. Can there be a theory of robustness in language models? And in my opinion, that question has these 4 aspects. Sensitivity. So we need to get a quantitative sense of how does perturbation in the input space affect perturbation in the output space of language models. Interpretability. Why are language models more consistent in certain situations versus less consistent in other situations? Trade-offs, any balance between consistency and other properties like fairness or accuracy, and also robust training. Specifically for robust training, is it possible to use robust loss functions? This is the exact reason that I started off and dove deep into the density power divergence based method. Is that this method is actually a generalization, like I mentioned, this is a generalization over maximum likelihood estimation. So it should be possible to extend empirical loss, empirical risk minimization in this robust paradigm as well. And hence, it should be possible to train or at least fine-tune language models using robust loss functions such as these. There are likely certain computational hurdles because of the iterative nature of the optimization I mentioned. But that itself is again a technical problem that we need to look deeper into as a community. The other problem that is worth looking into is local consistency, in the sense that if you consider training data of any learning system, be it language models or statistical models, that training data is a finite sample from a certain population, and there are concept-specific sub-data sets sitting in that large data set. For example, there can be data that is corresponding to medical question answer in the original data set. There can be data corresponding to summarization. There can be data related to banking related questions. There can be data related to Reddit threads. The original data set is diverse, but there are subsets of that data that are relevant for certain tasks. And so to ensure consistency for each of these tasks, there probably is some sample size requirement for those sub data sets. What are those sample size requirements, and how do they scale with the consistency metric that is under question? So these are all the details that I think needs to be figured out. And honestly, that is a complex problem. Language models are right now, as they operate, is that they can take in any input and take in any output. So they can solve, quote unquote, solve any type of task related situations, be it again medical questions or any other domain specific task. So for what tasks do they perform well, or what tasks do they perform not so well based on properties of the training data, and how can we optimize these languages by gathering good quality data, getting provable bounds for such performance metrics across different data sets and tasks. That is a rich area of research that I think is waiting for people to dive deeper into and propose innovative solutions. So these problems are something I'm thinking deeply about. Some of my existing research directions are along these lines. And yeah, with that, I'll conclude this talk. Happy to take questions, also discuss along these open directions as well. Thanks so much.
One remark. Can you go this 3 slides back, perhaps, where you showed the loss function you want to train the LLM? Yeah, this slide. This it's not just the iterative process that you make the training hard, but computing this gradient is also very hard, right?
Yep. You use stochastic gradient descent normally. So how, what are the changes that needs to be done in the different parts of the SGD process, like mini batch formation and learning rate changes? Yeah, those details are, those are difficult technical problems. You're right.
I've got like a very general question. So when you talk about theory of LLMs or anything of this nature, then if I want to do theory, then I guess one does need some model of language, right? Otherwise, not doing LLM theory, where is doing some other kind of theory. What model of language can one hope to use, or do you have any sense of that?
That is a good question. I think on that front, I can see a lot of variation across different languages as well. And so two things. Firstly, it's probably useful to start from actually three things. Firstly is that it's probably useful to start from English language-based situations to get some initial answers. Secondly is that the nature of the results that can be found would probably depend on the language that you are modeling, like compared to English to Hindi to Bengali. Thirdly, I think at the core of all of this is the tokenizer. For different language models, tokenizers can vary. And based on how the tokenizer is structured, everything changes, because based on how the tokenizer is structured, the initial tensor changes, the ending probabilities change as well. So that part needs to be taken into account somehow as well. Tokenizers are an under explored area in language models too.
Okay, I guess I have like one more stupid question. So can you go back to the experimental results for this, the table?
Sure.
Okay, so I guess there's just so something I'm trying to understand. So what is the thing with the underline and the bold? So what was that? So highest and second highest. Okay.
Yeah. So what I did was I fine-tuned using two data sets, small and large. We fine-tuned two models. So for each data set, under each metric, the highest consistency value according to a certain metric is bold, and the second highest is underlined. So the basic idea is that if this proposed method COG works, then you'd expect to find bold or underlined values under COG LoRa or COG SFT. So, yeah.
Okay.
Don't think there are any other questions, so let's move on.
Thanks so much. It was a pleasure.
Thank you.